The weather. Everybody talks about it,
High
and
temperature
everybody
today, not too
watches it.
bad, 48 degrees.
It seems to influence just about everything around us. And in the 21st century, we may become more affected than ever by global changes taking place in the Earth's atmosphere. The incredible power of weather shapes our landscapes, the production of our food crops. It enhances our outdoor activities. It creates conditions that can lead to uncontrollable fires. Or it can amaze us with its powerful destructive forces. Every night,
46 for your high today, and then look for the higher
millions
elevations
of
to see a
TV
little
viewers
bit.
tune into their evening newscast to glimpse the next day's weather. They are treated to colorful images of invading air masses and colliding fronts, changing cloud patterns that tell them tomorrow will be a great day for a hike, or that boarding up their windows, packing up their belongings, and heading for safety would be a smart idea. These predictions are made by scientists called meteorologists who study and predict weather 24 hours a day, 7 days a week. Meteorologists gather their data from weather stations on land, out at sea, from instruments sent high into the atmosphere, and research aircraft flying into the hearts of storms. They use giant radar dishes to track falling raindrops, and eyes in the sky satellites orbiting hundreds to thousands of miles above the Earth, providing views of hurricanes, thunderstorms, and the jet stream. Today, this results in a considerable array of data that has been gathered, recorded, and fed into computers. Here it is sorted, analyzed, and interpreted into futuristic visions called weather forecasts.
Here's the big twirl to our clouds and the radar. Counterclockwise, we've got ourselves a low. And as it
To
comes
find
up
out
the
more,
coast,
we've asked meteorologist Kim Martucci from Fox 25 News in Boston to help guide us as we embark on learning more about the world of weather forecasting. As inhabitants of planet Earth, we live at the bottom of a layered atmosphere consisting of life-sustaining gases that are almost always in motion. Without this sheltering blanket, our Earth would be as dead and unchanging as the moon. We can't see it, but our atmosphere has discrete layers. The layers of the atmosphere regulate temperatures around the globe. The lowest atmospheric layer in which we live is called the troposphere. It is here that all weather as we know it occurs. The troposphere extends upward some 10 to 15 kilometers or 6 to 9 miles from the Earth's surface. The next layer above it is the stratosphere. Here is where many commercial airliners fly. At the top of the stratosphere, 50 kilometers or 30 miles above the Earth's surface, we find the ozone layer. This thin, fragile layer protects our planet from the harmful effects of ultraviolet radiation coming from the sun. Above the ozone layer, another protective layer called the mesosphere occurs. Located 50 to 80 kilometers or about 30 to 50 miles above the Earth, it's here meteors burn up before reaching the ground. Our Earth gains about 17 tons in weight every day from the cosmic dust filtering down from these burnout intruders. That dust on top of your dresser may have actually come from outer space. Above the mesosphere is the thermosphere. This layer has no definite outer boundary. Here is where the aurora borealis dances across the sky. The sun is the single most powerful force driving changes in the weather. The Earth, like other planets, receives solar energy from the sun. As our Earth rotates on its axis, radiation from the sun warms the Earth unevenly, setting the troposphere into constant, turbulent motion. More solar energy reaches the regions near the Earth's equator. This causes the equatorial regions to heat up more than the poles. Warm air from the equator rises to the top of the troposphere, where it moves off towards the colder poles. This circular movement of air forms atmospheric circulation cells. These cells transport heat from the equator to the poles. If the Earth was standing still, and there were no oceans, the weather would be much simpler to predict. But it's not. The Earth spins on its axis 24,000 miles per hour near the equator, but travels at 0 miles per hour at the poles. This differential movement deflects moving air and turns cell patterns into wind belts in both the northern and southern hemispheres. Over the Earth, these prevailing winds generally blow steadily in the same direction. For centuries, sailors have depended on trade winds to get where they're going. These winds also influence our weather by pushing around large masses of air. The air in the tropics is very warm. It contains lots of moisture. Tropical winds blow these warm, humid air masses northward. Meanwhile, the prevailing westerly winds push cold, moist air masses from the Pacific Ocean towards the west coast. Continental polar air masses from Canada bring chilly, dry air down between the Rockies and the Great Lakes. Any or all of these air masses can then be affected by the jet stream. If they meet up with each other, disaster can occur. The story of the perfect storm is a great example of what can happen when a large cold air mass from the north meets a large warm air mass from the south.
But why is it called the perfect storm? It's called the perfect storm because it had three great ingredients. It had the cold, dry air, it had an area of low pressure, and it had the remnants of a hurricane. And it took meteorological perfection to make all these ingredients come together to make this monster storm.
As we've just seen, when large air masses with different temperatures and humidity come together, they can create severe storms. And, like clashing armies at a military battlefront, where two different air masses come together, it is also called a front. Fronts almost always represent an area of changing weather. A front is the transition zone between two large air masses of different temperature and density. In the weather world, there are three basic types of fronts: cold fronts, warm fronts, stationary fronts.
When you watch a TV meteorologist talk about this blue line with the triangles on it, that's actually a cold front. Behind it is the leading air mass of colder air. And as you can see, it's overtaking all of New England.
Cold fronts can move very quickly. When a rapidly moving cold front runs into less dense, warmer air, cold air is forced under the warm front. This forces the warm air up, and big cumulus clouds form. Because cold fronts can move so quickly, violent thunderstorms may result.
Warm fronts are these red lines with the little half circles on them. They always move in the direction that the circles are pointing. Behind this is warm air. It's the leading edge of a warmer air mass.
Unlike cold fronts, warm fronts move more slowly. We can often detect warm fronts coming many days in advance of their arrival by the output of high cirrus clouds that may lead to summer showers. In winter, warm fronts can bring snow, sleet, and freezing rain.
On this weather map, we've got two different stories. To the north, cold air, and to the south, really warm air. Since these two air masses don't want to move anytime soon, we're stuck with a stationary front right in between the two. You can see the blue line here with the triangle is back, and this red line with the half circle. And since this front isn't moving very much, we call it a stationary front. And below, we can get lots of rain that can sometimes lead to flooding.
Looking at the weather chart, we see large areas marked with H's and L's. Each L indicates an area of low pressure that have less air overhead than surrounding areas. Low pressure areas bring cloudy and wet weather. The places marked with H's are high pressure areas with more air overhead than places nearby. High pressure areas typically bring clear, dry weather. When we release the air from a balloon, the high pressure air in the balloon escapes into an area of low pressure air. This also happens when we equalize our ears, because the air pressure inside our heads is different than the air surrounding us. Winds are created from the movement of air. Weather forecasters often predict that a weather change is coming due to a shift in wind patterns caused by the jet stream.
This blue squiggly line on our weather map is the old jet stream. Did you know that it was discovered during World War II? Our aircraft were trying to fly west towards Japan, and they encountered these really strong headwinds, and they weren't making very much headway. This jet stream is also responsible for getting you from LA to New York almost an hour faster than if you were to go the other way. The jet stream separates the really warm air from the cold air at the surface, and sometimes they steer storms around the U.S. So when you see this big dip over the East Coast in this case, it's possible an area of low pressure will develop and maybe bring you some rain or snow.
An important part of weather is the transfer of heat from the sun. The sun warms the ground by radiation. The warmed ground transfers heat into the air above by conduction. As these molecules of air become more and more heated, they move faster and bump into each other and move farther apart. Because of this spacing, the air becomes less dense and rises. The upward movement of warm air and the downward flow of cool air form convection currents. On the ground, water vapor often condenses on cooler surfaces. The temperature at which air can no longer hold all the water it contains is called the dew point, and the air will begin to shed water. You've seen it happen when dew forms on grass and plants. When warm air containing water vapor rises through the atmosphere, it expands and cools until it reaches the dew point. When this happens, tiny water droplets condense around microscopic particles of dust and salt located in the atmosphere, and presto, a cloud is formed. A cloud is simply a collection of tiny droplets that have condensed in the atmosphere. These droplets are so small that it takes more than 1 million of them to form one raindrop. In the higher latitudes and higher altitudes where it's colder, water vapor crystallizes directly into snow crystals or frost. Besides rain and snow, clouds can also bring other effects too, like lightning. When unstable air masses form extremely violent thunderstorms, these conditions can lead to tornadoes. And even though tornadoes can be frightening and very destructive, of all the disturbances that create storms, hurricanes are the most devastating. The sustained winds of hurricanes can range to greater than 155 miles per hour. Hurricanes last longer than other storms, and their effects can linger up to a week or more. Seen from outer space, hurricanes often cover thousands of square miles. They typically form over warm waters of tropical seas in the Atlantic Ocean. They can travel and even strengthen over the Gulf of Mexico and the Caribbean Sea. When they form in the eastern and central Pacific Ocean, they are called typhoons. Hurricane tracking maps are often used by weather enthusiasts to follow the path of developing tropical storms and hurricanes. People have been observing weather for centuries, but efforts to quantify it are fairly recent. Scientists such as Galileo studied the atmosphere in the 17th century, using thermometers to measure the air temperature, barometers to measure changes in atmospheric pressure, and a hygrometer to measure the amount of moisture in the air. Amazingly, these three instruments are still used today. Forecasters rely on ground truthing, that is, the use of these traditional instruments to cross-check and verify the data gathered from electronic methods. Let's take a look at how 21st century meteorologists gather their weather information used to deliver the daily forecast. To be able to plan and predict weather, you must be able to measure atmospheric conditions as accurately as possible. Land-based weather stations dot the globe, but 70% of the Earth's surface is covered with water, so meteorologists also use data from weather ships and weather buoys to compile a comprehensive picture of global weather occurrences. Invented in the late 1930s by British naval intelligence to monitor enemy German aircraft, radar is used today by meteorologists to detect rain activity and measure its range. Virtually all of the tornadoes and severe thunderstorms over the United States are monitored by radar. On this radar map, we can see areas of highly reflective clouds indicating heavy rain. The less reflective clouds have light rain, and the non-reflective areas are clear. Doppler radar is a special type of weather radar that measures the direction of speed of moving objects like rain or snow, by determining whether the atmospheric motion is towards or away from the radar. Doppler radar is also able to detect the strong winds inside thunderstorms that can cause microbursts, a strong shifting wind pattern associated with large wind shears. Wind shears are monitored very closely due to the danger they impose to air travel. Here we see scientists launching a gas-filled weather balloon carrying instrument packages to profile local temperature, humidity, and wind. This data is radioed back as the balloon ascends into the stratosphere. Research aircraft like this one used by the National Oceanic and Atmospheric Administration, known as NOAA, routinely fly into areas of high weather activity. This plane is flying into the eye of Hurricane Edward off the coast of Florida. Beaming back constant information, weather satellites orbit high above the Earth, collecting data on the flow of water vapor or the movement of frontal systems. A satellite's orbital path can be geostationary, which means it maintains the same position over the equator during the Earth's rotation, like the GOES weather satellites. The first step in weather forecasting is finding out what the weather is doing right now.
This is what I do. When I come into work, I first come in and I acclimate myself to the current conditions, and then I'll start to look at the computer models. For example, one computer model's name is called the eta, which is a Greek letter, and it's also a variable that we use in math. And I'll take a look at what the eta says is going to be the forecast over the next 48 to 60 hours. And I can call them up right at my fingertips on the computer screen and see in color all the pretty maps that depict certain levels of the atmosphere. So this map, for example, is showing me what they think the jet stream will be doing by Thursday morning, which is tomorrow. Or I could come down and look in what the clouds are going to be doing by Thursday morning. The blue here means that it's going to be cloudy over New England tomorrow. I know that because down here, this key says the blue is 100% humidity. I can also look at where the storms will be. This map tells me that. So what I'll do is I'll look at this one computer model and I'll look at several more to the point where I have an idea of what all the computer models are telling me. Then what I can do is decide which computer model I think is on the right track. Because computer models aren't always right. They have biases and you learn what they are the more you forecast the weather. So I become a more accurate forecaster by looking at lots of things and even by making mistakes because I can learn from my mistakes. So that's basically what I do. I come in, I check all the computer models,